What's one of the best questions to ask when interviewing candidates for a site reliability engineering role? It's deceptively simple. Here's the question. What is software reliability? On the surface, it's a pretty simple question, but like an onion, many layers exist. This video will help us to do two things: define software reliability and discuss how to measure software reliability. While we peel this onion back, we'll chit-chat about how the relatively new discipline of site reliability engineering, or SRE for short, fits into the broader discussion of software reliability in the industry. The goal of this video is to help a site reliability engineer, or someone thinking of becoming one, to clarify the relationship between reliability, quality, design, and operational performance. First, we'll start with the simple definition of reliability, which will serve as a perfectly good answer to a question that comes up like this during an interview. Next, we'll take our general understanding of reliability and discuss how we can use this understanding to measure the reliability of software using service level objectives, or SLOs for short, and service level indicators, or SLIs for short. Finally, we'll tie these topics together by briefly discussing the importance of being able to share a story of how you've helped to improve the reliability of a system in the past. So, now that we know the mission, let's explore software reliability through the lens of a site reliability engineering team. Let's go. Before we attempt to answer these questions, let's think about software as a product. In this sense, we should be able to define reliability in general terms by coming up with some kind of definition of reliability for any kind of product. Let's give it a shot. For instance, what makes a car reliable? We might think that a car is reliable if it doesn't break down, but that's not exactly true. The owner of a Toyota Corolla might expect high reliability than someone who buys a Ford Mustang. While the Mustang may break down once in a while, the Mustang owner might be more satisfied with the reliability of their car because they wanted something that's high performance. They may have realized that performance comes with trade-offs, one of them being quality. In other words, a Mustang owner might feel that the car is less reliable if it starts smoothly but doesn't feel as powerful. On the other hand, if a Toyota Corolla idles roughly in the mornings, that symptom alone might be enough to make the owner feel that their Corolla is unreliable, even though they might still have a positive image of the brand's reliability in general terms. If the gas pedal is a little slow to rev the engine in their Corolla, you might simply think that the Corolla is efficient and smooth, rather than slow and underpowered. So, it seems like reliability is kind of like a subjective measurement of satisfaction with the behavior of a product. Is that true? Is reliability the matter of subjective opinion? Not so fast. In a life-critical system, unreliable software kills people. For instance, in an airplane, a software defect might be catastrophic, like the Boeing 737 MAX software defect that caused the nose to aggressively pitch up and pilots to lose control, resulting in 2 airplane crashes and 346 fatalities, according to the NIST. So nothing subjective about the poor reliability of a product kills people. In a business-critical but not life-critical system, reliability becomes a bit more subjective. A rough idle is different from a failing brake pedal. A customer might develop a subjectively poor feeling about the reliability of an entire system based on their experience with the single operation, but if we peel the onion back, can the engineering team responsible for a product measure reliability objectively within a narrow enough scope? If we measure the quality of many operations of a system, can we combine these measurements to come up with a good feeling of the level of reliability that customers will actually experience? With these questions in mind, let's take a crack at defining reliability. Carnegie Mellon University has a pretty succinct definition. Software reliability is the probability of failure-free software operation for a specified period of time in a specified environment. Software reliability is also an important factor affecting system reliability. It differs from hardware reliability in that it reflects the design perfection rather than the manufacturing perfection. There are a few very interesting nuances in this definition. First, is that software reliability is not equal to system reliability. When we use the term software reliability, we mean the reliability of a specific operation in a single environment. So let's imagine an e-commerce site. We might feel that one e-commerce site is more reliable than the other, but we can only measure that a specific operation of an e-commerce site is reliable or not reliable. For instance, adding a product to our shopping cart might feel generally reliable if only 1 out of 1,000 button clicks results in failure or some kind of unacceptable delay. But shipping products might be unreliable and slow if original estimates are always more optimistic than the actual shipping times that customers experience. Both operations are part of the same system, but one is a software operation and one is a more complex logistics process that involves many systems. Shipping also might involve a fleet of machines, everything from conveyor belts in a factory to trucks that transport packages. There's a difference between a single software operation and an entire e-commerce system. Second is that software reliability reflects design perfection. In other words, where hardware reliability depends on manufacturing perfection, software reliability depends on software design perfection. Therefore, we can basically say that reliability of software that doesn't reflect a purposeful design is accidental reliability. It's not intentional. In other words, reliability begins with the design phase, including architecture. Third is that the reliability of a software operation is related to a specific environment. A software operation that's reliable while running locally might behave differently after we migrate our system to another runtime environment. The migration from environment to environment may cause radically different reliability characteristics. Therefore, we can't assume that a software operation which is reliable in one environment is going to be reliable in another. So, with these 3 points in mind, is the definition from Carnegie Mellon still reasonable? Before we land on it as a canonical definition, it's important to understand that more formal models of software reliability exist in various industries. For instance, an association called the Motor Industry Software Reliability Association helped establish standards for embedded software systems used in vehicles, such as the MISRA C standard, which is basically a set of programming rules intended to ensure that C code used in vehicle systems avoids runtime errors through poor programming practices. Say that fast 3 times. For a Rust programmer building Linux CLIs, this definition has very little to do with us. But if we're a C programmer that specializes in building embedded systems for cars, we should probably know and be able to cite the MISRA C standard. So, if you're interviewing for an SRE role related to a specific industry, it's important that you research and study any standards that might apply. Let's add a 4th point. The standards of software reliability vary wildly between industries. In terms of general understanding of reliability, and for the majority of cases, most SRE managers would be quite pleased to hear a quote from Carnegie Mellon if asked about a definition of software reliability. So, for the purpose of this video, let's settle on that definition of software reliability. So again, software reliability is the probability of failure-free software operation for a specified period of time in a specified environment. Carnegie Mellon nailed it. Good job. Now that we have a definition, put it in your pocket. If it comes up in an interview, you'll be ready. Now that we understand the textbook definition of reliability, we need to bridge the gap between our textbooks and the complex real-world practice of building reliable systems. Software architecture is a huge field to study and impossible to encapsulate in a short video, but we're going to cover a few basic concepts that can have a huge influence on the reliability of a system. It's worth noting that we'll be using the term system quite frequently from here on out, not only in this section, but throughout the rest of the video. Even though we measure reliability at the level of an operation, which we'll cover in more detail soon, it's important to note that software comes in systems. On a technical level, we may design and implement functions, services, libraries, and components, but customers care about their experience, not our technology implementation details. Remember when we said that software reliability depends on design perfection? When designing software, we need to achieve design perfection at a systems level. A single operation that performs flawlessly means very little to a user if all other operations in the system are completely unreliable. To make this concept more clear, let's explore Twitter's high-level architecture as an example. Twitter is composed of many different systems, subsystems, services, libraries, and individual operations, which all must work together properly to achieve some kind of good user experience. Imagine a scenario in which two-factor authentication breaks. At that moment, the reliability characteristics of Twitter's timeline becomes less important to users that can't even log in. As technologists, we need to care about the reliability of single operations. But really, our users care about the reliability of entire systems and subsystems and how they all interact with each other. With this in mind, throughout the rest of this video, we'll use the term system to describe important boundaries in a larger software product. For instance, in a product organization like Twitter, one team may own an authentication system, whereas another team may own a timeline system, and a third team may own a search system. In order to create a metric for the reliability of the entire product, we need to think about how operations are implemented within each system boundary and how various systems interact with each other. To start bridging the gap between individual operations and systems, let's look at two of the most important architectural considerations at a systems level: availability and consistency. The availability of a software operation is typically measured by a percentage and counted in nines. So, for instance, 2 nines means that an operation is 99% available. In real terms, this means that the operation can be unavailable for up to 14.4 minutes per day. So it'd certainly not be high availability, or HA for short. But this type of downtime was pretty common in legacy systems that required downtime to perform maintenance. Think of an operation in a banking system, like viewing your account balance. You might try to log into your online banking account and see a maintenance page that online banking is currently unavailable. And that might last all night. Welcome to 2005. This means that by all intents and purposes, your current balance is unavailable online. Remember, we have to consider the environment. Maybe your bank account balance is available over the telephone banking system. Who knows? Banking systems were a mess. But consider this. As long as the maintenance that took online banking down for that night was kept under 14 minutes, any affected operations would still achieve those 2 nines of availability. So, if someone says that their system is 99% available, that means it's available for all but 14 minutes per day. Is 2 nines bad? Not really, not unless we require higher availability. If the cost of increasing availability is higher than the additional revenue that higher availability might generate, a business doesn't really need to invest in more nines. Keep in mind that every 9 that we add to a system might be extremely costly to implement, might require a major refactoring or re-architecture of the system. For instance, a system with 3 nines, which means 99.9% availability, can only have 10 minutes of downtime per week, not per day. If the only thing causing unavailability are the maintenance windows required for a new release, why not just release less often? Well, that'd mean bug fixes and new features would be held back from users for up to 7 days. We can actually push this type of compromise further and further until we're only releasing quarterly, which is actually what many companies used to do back in the day. Probably still do, actually. Holding back new features from our users for an entire quarter probably doesn't make any sense. The alternate approach is to invest heavily in our systems to keep availability high and deployment frequency high as well, which is why it makes sense to improve availability for users need additional availability. Go figure. Think about this. As we add even more nines, the engineering challenge becomes exponentially harder. A system with 4 nines can be only unavailable for up to 1 minute per day. A system with 5 nines, unavailable for up to 5 minutes per year. Systems with 9 nines can only be unavailable for up to 31.56 milliseconds per year. We're counting decimal places at this point, meaning that any failure in such a system must be detected and self-healed almost instantaneously. Such systems are very rare indeed, and typically limited to life-critical infrastructure. Even at 5 nines of availability, it would be virtually impossible for a human to manually troubleshoot an issue, because acknowledging, investigating, and fixing a single bug or alert would take a human being probably a lot longer than 5 minutes to complete. Even if the speed were possible, A system with 5 nines can have only one incident per year that takes longer than 5 minutes to manually troubleshoot and deploy a fix to resolve. So, work backwards, and we can see that a system with anything beyond 4 nines of availability must be fully self-healing, involve no manual operations, and be flawlessly upgradable with zero downtime. It might be pretty obvious to see that high availability systems require some serious software architecture and some pretty serious and intentional design decisions. So what does this all mean? Well, if a business doesn't require a system to be HA, that means we probably shouldn't waste significant capital to implement full self-healing. Many systems only require 2 or 3 nines of availability, let alone 4 or 5 nines. While availability and reliability are not one and the same, availability is an important part of reliability engineering. Early in my career, I was a big fan of over-engineering for availability, but in my old age, I've learned some valuable lessons. Now that we've covered availability, the other piece of the reliability discussion is the consistency of data. Highly available systems often achieve high levels of availability by trading off for consistency. For example, rather than integrate directly with a third-party system, a highly available system might cache data to increase reliability and only use locally cached data. This might make a system highly available, but the data might not be perfectly consistent anymore. Cached data grows stale over time, and the decision to show stale data might be worse than the decision to simply show a user an error message. It all depends on the context of the business, and these are part of design trade-offs. Why discuss consistency as well as availability? Well, if you remember, our definition of reliability is that it's a reflection of design perfection. Part of this design perfection must be discussing availability and consistency considerations in order to achieve the reliability of an operation. Another way to look at reliability characteristics is through the lens of the Reactive Manifesto, a high-level set of principles that frames software design by focusing on the outcome we wish to achieve, producing responsive products and systems. A responsive product is both maintainable and extensible. The Reactive Manifesto uses the term resilience to loosely represent reliability, which must be paired with elasticity in order to achieve responsiveness. Let's imagine an e-commerce site again. This e-commerce site receives a big spike of traffic or a sudden increase in users. In order to remain responsive, the new system must be elastic to the spike of traffic, perhaps even by provisioning new servers in real time to handle the additional load. The system must also remain resilient in the face of individual failures in single operations. This avoids large cascading failures that can take down a whole product. This was a crash course in what it means to achieve design perfection. Even though software architecture is a complex field that requires study and experience to feel comfortable in, learning the basics can help anyone in any technical role to ask really important questions, and these questions can really influence the reliability of the systems under their care. If you're interested in learning more, I'll link a bunch of resources in the description of this video. Now that we've discussed what reliability is and how reliability is influenced by design, let's discuss how to measure reliability using 2 techniques: service level objectives and service level indicators. If you remember earlier, we defined reliability as the probability of failure-free software operation for a specified time in a specified environment. SLOs are a way to quantify reliability into something measurable that we can communicate out to our team using numbers or dashboards. SLOs are reliability objectives and commitments. SLOs are ideally how you measure reliability from a customer-centric perspective. SLIs are measurable reliability indicators, which are the input into SLO computations. SLAs, which we haven't discussed yet, stand for service level agreements. They actually have very little overlap with SLOs and SLIs, but these 3 terms are regularly conflated, especially during interviews. SLAs define the level of service expected by a customer from a supplier, laying out the metrics by which that service is measured, and the remedies, or penalties, if any, should the agreed-on service levels not be achieved. So think about it this way. By the time you're discussing the nuances of an SLA with a customer, it's a pretty bad situation. Your system is probably failing to meet their expectations, so now it's a question of what the penalty is. To avoid this customer experience trap altogether, let's discuss an analogy. Think of SLAs like a contract to purchase a new vehicle. SLOs are like the vehicle manufacturer's targets for the reliability of the make and model of the vehicle that you purchased, but are part of their internal design process, not necessarily communicated verbatim in contractual terms. Typically, companies aim to vastly outperform against contractual terms to avoid penalties. Now, SLIs are like a car owner's actual day-to-day experience with the car that they actually bought, and they'll communicate this experience to the dealer during service visits. Let's look at SLOs through another lens, an e-commerce site. Imagine one of the most fundamental features of an e-commerce site, which is submitting an order, sometimes called the checkout flow. The actual logistics of the checkout flow might be complicated, like collecting payment, finding items in a warehouse, packing those items, and shipping those items to customers. But in terms of a customer's experience, we want to make sure customers feel that the entire end-to-end process is reliable and responsive. One of the easiest ways we can build trust in the entire process is to acknowledge every new order in a timely fashion. So let's say that our goal is a responsive user experience. With this in mind, let's create an order acknowledgement SLO to help all service owners have a conversation about their expectations up front. In this example, we decide to acknowledge new orders within 2 seconds. This is the design time part of SLOs. When we're designing a new feature, we should talk about all key operations of the feature and set clear service level objectives for each of those operations. This gives us a chance to explore reliability expectations up front to make sure they're technically reasonable, and either commit to these expectations or evaluate compromises and alternatives. After we move the checkout flow into a real production system, we can actually measure the real-world performance of order acknowledgements. By counting every order request and computing the latency between button click to order acknowledgement, we can aggregate real SLO performance within the window we decided during design time, in this case 24 hours, and report on this performance window by window. In this example, it looks like orders are not acknowledged within our 2-second objectives on some days. This is an early warning signal that we have a deeper investigation to do. Keep in mind that SLOs do not replace other types of operational visibility like monitoring, but with enough SLOs in place, they can point us towards potential hotspots of decreasing reliability. This is a complicated topic. We have another video coming out about SLOs that will help us dive deeper, so subscribe to be notified when it's published. But this high-level overview should give you a broad understanding of SLOs. At a high level, SLOs can be used to help improve reliability by making sure that service level objectives are set during design, measured in production, and reported to stakeholders, so the right changes can be made to the product. Let's close out this topic with a few interview tips related to SLAs, SLOs, and SLIs. I recommend studying SLOs and then form your own opinion on how to best measure the reliability of software without having to index too heavily on SLAs and contracts. I'll actually go one step further and make a very bold assertion that site reliability engineering is actually impossible without SLOs. Software reliability is a reflection of design perfection, and it's impossible to achieve design perfection in a software system without designing the system around a clear set of reliability objectives. It's kind of like a car manufacturer not setting reliability targets for a new vehicle model and simply hoping that whatever they produce is going to be reliable. It's basically impossible in manufacturing and no different in software, in my opinion. But let's conclude this video by answering our original question, which is, how do you define and measure reliability? First, reliability is the probability of failure-free software operation for a specified period of time in a specified environment. Second, design perfection must be achieved at a systems level. At best, reliability is accidental without intentional design. A system that achieves high levels of reliability within reasonable time and budget is the result of design perfection. Third, we can measure reliability using service level objectives, or SLOs for short, and service level indicators, or SLIs for short. A parting thought is that SLOs should influence future design decisions. The real value of service level objectives are the feedback loop that they help us to create in our systems. They provide us with real-world insights into the reliability of our systems through the eyes of our customers. If we bring these learnings back into the design of new features or changes to existing features, we'll continue to improve the reliability of our systems over time. Perfection can only be achieved with real-world data, and perfection often takes time. Many factors go into the design of software, but reliability must be a core consideration of design decisions. To conclude this video, I'll leave you with a question. If you're interviewing for SRE roles, do you have a compelling story of a reliability improvement that you've personally championed and implemented in the past? How did you measure the net impact of that improvement? Did you use SLOs or did you use another technique? Whatever technique you've used, make sure you can describe the details. Think of concrete examples of how the technique you've used has helped improve the reliability of a system under your care. So that wraps up our video on my favorite, deceptively simple but ultimately complex SRE interview question: what is software reliability? We peeled that onion way back, and I hope your eyes aren't watering too much. Thanks for tuning in, and I hope this little bit of advice helps you out on your SRE and software development journey.